and as great as it is today. In doing that, Patrick has touched on virtually every topic that has to do with power grids, and most recently on aspects of machine learning and how it can interact with operations. So Patrick, you have the floor. Kevin is in charge of the time. And I think in about 45 minutes, we'll try and take some questions if there haven't been any before. Thank you.
Thank you. Thank you. Yes, it's a pleasure to be here and to share some vision, some ideas about that. And I have a lot of materials, but I will go fast for some part. So the idea is that, yes, we are speaking of power systems. They are very large things and perhaps the most complex machine ever built by humankind. And of course, I was used to work on this part of the European system and with RTE. Now I am in the way to be retired. So the outline of my presentation will be to give a small introduction on this is a complex system, some idea of this decision-making problem in operation for this large system, and something on mixing machine learning and standard optimization techniques, and with some example on topology optimization. And then the discussion more kind of what could be a foundational model, or is it possible to have a foundational model to do something in power system? So yes, managing complex systems. So people like RTE, they are TSO, they are managing, and they're also the transmission owner of the transmission and sub-transmission network in France. So I mean that S5 voltage for 400 kV and also the sub-transmission. And the distribution in our other company, more or less only a big one in France, and of course a lot of happen now in the sub-transmission grid. Yeah. So the S5 voltage is more for interconnector with the rest of Europe, some very large power plant, and some industrial customers that are connected to this S5 voltage, including some railway and things like that. So on a medium S5 voltage, we have some smaller power plant, in particular wind and solar, and that are connected to this level, and also many of them also connected to the distribution system. And in the distribution system, now the consumer have some PV rooftop and EV charging and everything, so they are more active than in the past. So this is something that changed a lot also in the complexity of the system. So yes, but power systems are very complex system, and we have this very recent blackout in Iberian Peninsula. So it's something that is quite new as a blackout because they were exporting a lot. You know, it's not something in the past when we have some blackouts, the people were importing or something like that. In this case, it was a bit strange because they were exporting, and they were exporting to France, they were exporting to Portugal, and there were also a lot of hydro pumping in the system. And then suddenly, yeah, something happened at around noon, and then everything collapsed, and they have a complete blackout. Yes, in most of Spain and Portugal. And of course, before the blackout, there was a lot of solar in the system, PV and a lot of wind, and not so much, but a lot of solar, and a few nuclear power plants and a few nuclear gas turbines. And of course, as yesterday, it was presented that everything was very bad, and there was a lot of interruption on many activities. It was impossible to pay by credit card. It was impossible. The water supply cut off. The traffic light was over, and elevators were not in operation. Metro and train were shut down, and even the airport. So there is a NSOE report that gives some idea on the factual, but I take a few information about that. So the idea is that at 12:32 on this day, there is an initial tripping of around 2.1 gigawatt of PV located in the southwest of Spain. And then in the following minute, everything collapsed, more or less. And then at only perhaps 1 minute after, a bit less than 1 minute after, there is a disconnection from France because we have some protection on on the line. When there is a loss of synchronism, we open the protection, and we believe that that perhaps avoid propagation of the blackout to the rest of France and perhaps Europe. Then everything become even worse because then they were isolated, and then some nuclear power plant also stop the remaining one, and more photovoltaic and everything. So at the end, they lose 20 gigawatt. And then for the nuclear power plant, we have to remember that when they stop, it's impossible to restart them for hours. And it is, in France, we are very concerned with that. We know that. This is why we are very afraid of blackout in France. And we have this defense plan that try to create some island to keep some energy in some area to avoid that. And then the blackout, lasts up to 10 hours to restore 60%, and 23 hours to have the complete restoration. But it was already a lot for the society and all the media and everything. And if this thing will last more, I don't know what will be the impact on society. Then there is quite a nice analysis from EPRI. You can find it in the web. So that is a YouTube thing that give information that are quite factual, and because we don't know the exact cause for the initial tripping. So the rest is more or less clear, but we don't know why we lose this 2.2 gigawatt at the very beginning. So big PV farm, and perhaps a lot of PV roof panel in a distribution grid. So there is an NSOE group that try to understand that, and we need more data, and the chronology is very important. We need to have something that, so it's under investigation. So, but there is this EPRI things. So yes, the system are evolving a lot. Once again, yes, there is this massive integration of renewable energy. So the marginal costs are zero. The fuel are for free. Yeah. Yes, both, yes. A lot of, in the southwest of Spain, there is a lot of, so it's very sunny and very, so yeah. So yes, so the fuel, yes, is a question, and the intermittency, but also the fact that they are connected through power electronic to the grid. So that changed a lot. How do we have to think about protection, control, and optimization of this power system? And there is something even more interesting, that because of this low controllability of the renewable energy, we think of installing more storage devices like batteries, but also demand response, so that these assumptions are very, very different with the basic assumption we have in historical design. And we say in all the textbook, it's not possible to store energy, demand is inflexible. So there is a urgent need to rethink both economics and dynamics, and including this reliability and resilience issue. And the effort we made, for example, for the nuclear power plant in France, we did that yet for the sun and the PV, the PV and the wind. And perhaps it's also because there is not anymore any integrated company like EDF that did that. And for example, with the grid code we have now, I'm not sure that we install all the PSS we are on a nuclear power plant. So it was designed in EDF, but with the grid code, there is no requirement to install that. So I don't know. So yes, so we need a lot of tools to try to assess all the decision, to help to assist all the decision-making process. Of course, for all the life cycle of the power system. So I mean from the infrastructure development to design, control, and protection, for the operation and maintenance. I want to focus more on this, on the maintenance thing. And then what we want basically is to optimize something, through some market or something. We want to minimize some cost, ensuring some security or some safety. And of course, to implement that, we need some control, and ensuring some hard constraint for the control. And to do that, we need to perform some simulation. And to perform the simulation, we need to have some modeling. And to have some modeling, we need to have some measurement. This is a need, but then we have coming back to reality, it's not possible to measure everything. It's not possible to model everything. It's not possible to simulate everything. It's not possible to control everything. So there is a kind of needs and and limitation of what we can do. So we are in this very complex decision-making process. So I want to illustrate a few conceptual high-level ideas about what we are doing in this optimization layer. So we want to have a look-ahead decision, so in advance, to be robust to uncertainty. So the fact that in a classical optimization, so we have this, we try to minimize something, so we try to find an optimal solution. So without constraint, it's easy. With some constraint, we have a feasible domain, so we find the solution, of course, in the active constraint of the feasible domain. And then it's a look-ahead thing, so we have some uncertainties. So the idea is that we have an expected optimal solution, but we want to be robust around this expected solution with a certain uncertainty set around this red circle. And so if you want to be robust to all the points in this circle, you want to take some margin for the expected value to be sure that for any point in the red circle, you are in the feasible domain. So we understand that if the uncertainty set grows and grows and grows, so the feasibility domain on expectation will reduce, reduce, and reduce. So it's not. So we have to do something, and the something that what we are doing, we try to put more and more closed-loop embedded system, because in this case we have some expected value, we have the feasible domain, and then this then if we have some realization of certainties that we go in a red point that is outside, we have some embedded controller that can bring back the point in the feasible domain. So that means that this black point that is not feasible, because this red is outside, become feasible because we have the controller that can do something for you. So this is the main idea of what we need more closed-loop embedded control, because we operate only after the uncertainties has been realized, so allowing a larger feasible set on the expected value. So we increase this feasible set because of this control. So if I want to, so we have this conceptual idea of these three layers to control, to manage the system. So we have something to protect. So we try to protect the people and the equipment using some very fast controller, very fast protection that act very, very rapidly in order of magnitude of milliseconds. So they are very simple. And then we have some controllers that act automatically in order of magnitude of seconds that try to ensure that we respect some nominal range for different variables. So for example, we are used to do that for frequency, for voltage, but what we want to do is something also for congestion on the line. So we have some idea we already implement that. So we have some area around 10 substations. So we can try to use some closed loop corrective controls that try to curtail wind and PV, for example, or to use some battery to try to control the congestion in this area. And then, of course, we have this optimized layer that go from days to minutes. It's more connected with the market. So we try to minimize something, cost or something. And then we try also to create some set point for the controller. And then also we can have some coordination between the controller through the set point we are sending. And then we have this analogy with the car. So the optimize is more this waves thing that try to find a good itinerary, more trajectory. So it's a big vision at the French level, for example. And then we have the zone that are more or less the analogy with a car. A zone is a car. And then we can think that the zone must be in some nominal condition and also interaction between the zone. So it's a self-driving car. And then we have this protection that is more an airbag or to try to avoid to kill the driver or the passenger, or even emergency brakes that try to avoid to crash a car. So this is the analogy. So this problem, so the optimization layer, this problem is very complex. So we want to minimize something to find this UP on a look-ahead thing. So we want to find the UP from T0 to T0 plus H with some constraints that are the system dynamics. So there's a differential algebraic equation. X and Y are state variable. UC are the embedded controller. UP is what we want to find. And W are the uncertainties. So W are the uncertainties. And then we have some embedded controller. So this policy pi is predefined. And then, for example, the MPC we have an MPC. We know that it's an MPC, but we can change some parameters that the set point or perhaps some other parameters that are the UP that we want to find in optimization. And then we can have a risk criterion here I put a chance constraint or some soft constraint that we want to have with high probability, some constraints that are satisfied. And of course, it's depending on the UC and on the UP. So we want to solve this problem that is just impossible to solve. So what we are used to do is to perform approximation and ad hoc heuristic based on the physical characteristic and temporal. Yeah. What do you mean?
What probability distribution?
So we have, so there is a lot of question. Now we are more doing some robust thing. So we are not doing some probability like that. We are more doing some boxes. Yeah. But then there is, but there is a lot of question about the boxes because we want to capture the spatial correlation. And so we have a reuse space, and we have a lot of questions how to compute that. So because but they can be too conservative if we put some, because we have some correlation between the error, the W. So we need to so we have a kind of PCA, bonded PCA. so that's why to reduce the number of variables, but keeping some limit. So, but we are working on what could be this probability, and in the past we have different R&D projects to try to do something like that, but it's a bit of an open problem. So yes, we are simplifying a lot. So we have this singular perturbation. We say, okay, the fast dynamics are stable, so we don't care. We just try to also to manage the steady state, so we can perform a relaxation or restriction on the feasible domain. Of course, we are using some DC approximation, things like that. We can do some kind of surrogate or proxy for the model. Of course, we can do some kind of decomposition, for example, of the graph or something like that. And I put just one example that I am working on that for several years, and say, okay, because sometimes we solve this ACOPF on the steady state, and then it's impossible to find trajectory to go from the local to the global point. So then I developed a small example on the WB5 thing. And then yes, I spoke with Bernie, and then Bernie found a solution, but an ad hoc solution for this example. So it's not a generic solution, but and it's a bit constitutive. You have to go in the other direction before. So then for me, it's quite an open problem to try to put this the existence of the trajectory in this problem. So, but yes, so we are performing a lot of approximation and heuristics. So for me, using machine learning to have better approximation and heuristic is not a big problem. It's not, anyway, there are approximation and heuristics. So it's not. So yes, so mixing machine learning and standard optimizations is a good way to go, and I try to formalize that like that, so we can put some optimization or machine learning before the optimization, inside the optimization engine, or after. Yes. So the idea is that we can use optimization before, for example, doing some graph clustering to decompose the problem, things like that. So we can do something inside, and we'll come back to have this, to learn how to do this bound and branch and bound in the mid, for example, but we can have some other idea, or we can use something that is a bit different than what we are doing here, but the idea is that we use an optimization by the relaxation, and then perhaps it's not feasible, perhaps you can use machine learning to ensure the feasibility, so it's a bit the reverse of what you are doing there, but anyway, this is the idea. So once again, I want to speak a bit of this grid topology. Of course, the topology is changing. So we have the power line that we can open or close. And we are also the substation. In the substation, in fact, when we have one electrical bus like that, in fact, internally, we have some breakers or disconnectors with this dot line. Then we can open them to have different kind of configuration. So it's not only about opening line, it's also to create new nodes and create new electrical buses. So of course, any method that have no knowledge of the grid topology will do something wrong. And of course, the topology changing, even if we don't want to optimize it, because we have some maintenance, so we have some planned outage, and we have some fault in the system, so we have some unplanned outage. And of course, there are also very efficient action levels in the system. So if we change the substation configuration or to perform optimal switching, so we can have a better solution. And for us as a TSO, it's quite easy because we own the breakers, and so we can do what we want. So we don't have to have a contract with the transmission owner or something to pay to do that. So it's also something that is good because we are a TSO. So for me, any machine learning approach must take into account this grid topology to do something good. And then, of course, we for several years we were in this try to do something, and then we say, okay, the fully connected neural net are not very good to do that, because and many papers sometimes they forget to explain that they are doing something for one given topology, and they need to rerun all the learning and everything when you change the topology. So this thing is perhaps not very possible for a real application. And we have to remember that the power grid is a graph. So the graph, there is a number of nodes, there is some adjacency matrix, and there is some B's that are the injection at the node. And then, for example, you have an output that could be the voltage at each node, but we can have also the flow on the line. And then, of course, the structure is more complex than just a vector or perhaps an image. Something is a graph. So any tentative to try to do something flat creates some problem because it's not anymore invariant by permutation and everything. So it's very hard to generalize and to find something good. So okay, so we had to look to this GNN, and then we can mimic in the machine a latent representation of keeping the same connectivity than the grid. And then we can create some latent variable on each node, the H1, H2, Hk. And then we can iterate to learn how to propagate information on this graph. And we learn some neural network, psi and phi, to try to perform this kind of propagation, this message pass. So we learn these two neural networks here, using the injection on the node, the adjacency matrix as parameters. And then we can decode, for example, for the voltage. So we have another neural network to learn after k-bar iteration. And then what we can do some machine learning that try to find the theta, all the parameters of this neural network. So on the expectation, not only on what the people are doing on the B, just on the injection, but we can also have some kind of randomness on the graph. So we can so all the G could be sample. So it's more, there is more information in that, and we hope that can be generalized for more graph and everything. So we learn something more than just an imitation of one single solution, but a large family of problems. So the idea is we can perhaps mix this machine learning based on GNN with optimization for this, for example, topology optimization. So I developed a toy example, yes, some time ago, to say, okay, even in DC approximation, so I create this example that I create two zones, and then I try to maximize the exchange between the left and the right. So I increase the generation on the left, I increase the consumption on the right. And then I try to change the topology to maximize the exchange when I just have the scalar variable lambda to increase everything. And then I create some fictitious substation. All the edges are double line. And the substation, if you have two neighbors, you have only one breaker to load and to generation. If we have three neighbors, you can have this different bus bar, so with different breakers and four. So I put this fictitious thing inside, so then it's possible to solve it as a mixed integral linear programming because it's a DC approximation. So it's 87 binary variable in this case, and for some instances that take 2 hours to solve this thing. So you know, even if I try, because there is a big M and everything, so I try to do some job on that, and also to add some constraints, for example, for the n-1, to keep connectivity for n-1 and things like that, to reduce the complexity. But okay, I couldn't find anything good. And of course, this will be impossible for several thousand substations. So yeah, so the idea is that perhaps what we can do something based on decomposition of the system, because we have this intuition that perhaps the configuration of one substation are not a lot of impact far away in the system. So it's quite intuitive, but could we decompose the system in quasi-independent zone? And the idea is that perhaps yes, because as I said, we have this SY voltage level, we have the high voltage level, and then we have some connection with the distribution grid that I call D node. And then we have this kind of structure that we have a network that connect everything, and then locally you have some redundancy, but there are some local redundancy. So perhaps we can decompose things like that. So we can have different zones that perhaps are not very much dependent, even if, so we can choose some zone with some minimal overlaps like that. And then if we're able to do that, perhaps we can do something. Of course, there is a lot of question. What means far away? So we developed a first approach, yes, for line switching, and Noureddin did a PhD on that, and so it was a nice contribution. So in this case, we were doing graph clustering, unsupervised machine learning to find this clustering. And if we have that, we can have a heuristic or an approximation that will say what I can do if for each zone I can solve the problem. With a simplified model, I keep the binary variable for the inside. I relax the external variable as continuous variable. So I will find this topology, TK, for this zone. And then I freeze the configuration for the non-overlapping substation. And then I can compute the topology for the overlapping substation as a MILP. So it's a MILP for the, but just for the internal thing, and the rest is a relaxation. And then I can do the thing just for the overlapping solution as a MILP. And then hopefully, if I aggregate the two topology, I hope to find a topology that is the same that if I was able to solve the big problem. So this is the idea, and of course we need to have a good enough decomposition, and perhaps this is not so easy. So we hope that this kind of idea can with this we can try to solve very large optimization problem. So this was something before. So inside is quite obvious here. So because we have a so it's a mixed integral linear programming. So the Y is a binary variable. So in this kind of mixed integral linear programming, you are relaxing and then you are branching, and then there is a lot of possible branching heuristic. And if you're not asked, you have Gurobi, and you don't say anything, they would choose something. We don't know exactly what, and based on some analysis of the problem, we don't know. But what we can do, we can randomize this option, and then we can learn what is the best option for us. So the idea is for one specific problem, we can learn what is the best option using machine learning. So the idea is that because we know that for instances and for the similar problem, perhaps we can find something better than the default solution from Gurobi, for example, or for Cplex. And the idea is we can use perhaps a GNN to do that for this topology. So this is one idea. I just start to begin that myself, so I don't know yet how it goes, but this is the idea. Then also inside the optimization engine for IC optimal power flow, we know this relaxation that give a SDP because we are relaxing the rank. So we have to solve this SDP problem on W, and for large system it's just impossible. So we know that if we have this click decomposition, because we have we perform a control expansion, we know that we can replace the big positive semi-definite constraint on the big W on smaller submatrices with some overlaps. And then there is not a unique control expansion, so we can try to learn which control expansion is a better one, using the solver we want to use. Because depending on what we want to solve the problem, using some interior point method for the overlapping, or RDMM or whatever, perhaps the control expansion could be different. So it's not a mathematical proof, it's something that is very practical depending on the algorithm you are using for solving. So I think, once again, that that could be something that could be interesting and worth to be continued. And then something, just an example of what we can do after. So the idea is for this topology optimization, so we can perform this DCOPF with this relaxed version of all the binary variable. And then we can try to solve it, if we are able to solve it with by imitation. So for medium-sized instances, that is the one we have, we can learn the GNN to try to perform the round-off, in fact. So this is the idea, that we can learn the GNN that try to use the continuous variable and to find the binary variable doing that, and with the hope that for large system, the generalization will be good enough, because for the large system, we are not able to solve it. This is one example. And then of course, we are using DC approximation, so there is no EC feasibility guarantees, but we have to recall that we have many levels for the voltage. To control the voltage, we have the capacitor bank, inductor banks, transformer, step changer, set point, generating unit voltage magnitude set point. So people forget about that when we are performing AC, we need also to change all these variables. So we have a project for a given topology, try to learn to do that using a GNN for a fixed topology. So we have some work, Balthazar did a PhD on that, and now we are very close to put in operation in RTE. So because GNN could have some drawback, but voltage is quite a local thing. So this example was, I think, a good possible solution. But then the idea is to put everything together. So the idea is that we can perform this GNN to try to find the topology using a DC approximation. And then for the fixed topology, we can use the GNN from Balthazar to find all the parameters we need for AC. And then we can try to solve the AC power flow. And then if it's feasible, we are happy. If not, we're in trouble. So then if not, we should change the topology. So we have to do something to iterate, or to do some end-to-end learning process that is a bit. So I want to push first this kind of thing, and then we'll see that if we need to iterate. And we know that sometimes we have to open some line in case of very high voltage. So I know that this thing could occur. But I want to continue this idea. And the idea is, rather than to put everything in a gigantic thing, to try to decompose. And even for explainability, for the operator and everything, I think is much better. And then also now we try to have that in operation. So if we are able to do that, we can, we don't have to repeat everything every time. We just have to have new module and to try to find it. So yes, my conclusion is that for this part is that it's good to combine domain knowledge, so power system expertise, yes, optimization techniques, and some machine learning and unsupervised machine learning to try to solve this very impossible problem. Then I want to share with you some more general idea on, is it possible to have something that could be a foundational model for power system or not? We know that many people try to work on that or to push some idea around that. But so I want to clarify perhaps what I think. And my question, is it something that is achievable, or is it just a a conceptual dead end, so it's not completely clear yet. So the idea for me is the definition of this foundational model is something that can use many diverse type of data, a lot of data at scale, and then with a very little adaptation for any specific task, and no, perhaps, training for specific tasks. So we put all the things we have. We can have some time series, some data, some text for anything, for the rule, for result of optimization or whatever. You put everything as an input, and then you try to ask any kind of question, load forecasting, renewable prediction, optimal dispatch, or whatever. So this is too large for me. So the idea is that we are not yet here. So what we can do now is more to have some problem-specific goal. For example, we can do something for forecasting, for load forecasting, for solving a COPF, perhaps, to tune a PSS to dampen error oscillation, but no power system expert expect that the same big model will do all that. But perhaps we can find something. Yes, so I pick also some idea. I was very in line with what David Rodnik was saying in this Science Day in France, the summit. Yes, so I took some idea, but the idea is that, yes, we need first to go for this problem-specific application, and to when we want to perform real task thing, and we can have some domain knowledge for the evaluation, and also to give more information to the machine learning, so it's more physically inspired. But perhaps we can have a first idea of what we can do. Perhaps that if we have a GNN, we can have a latent representation in the graph, so this H. And then for different kind of optimization problem, we can have some decoders that try to find the optimal, for example, unit commitment, or the optimal amount of location of primary frequency reserve, or the optimal grid topology. So it's not everything, but some type of problem, perhaps we can hope to have that as a first kind of, but for now, what we try to do is just a specific encoder for each application. We have some first attempt to do some transfer learning. For example, we try to imitate AC power flow, and then we try, for example, to do this voltage control, starting from that. So we find the encoder for the imitation of the AC power flow, and then we just try to tune the decoder for the voltage control. But for now, it's not very good. It's better to try also to learn the encoder also for the voltage control rather than to. So we are still very far from a foundational model. And then the question about LLM. So perhaps for me, there is a possible application that is a front end between human and very complex dedicated application. So the idea is that there is a big thing, an elephant here, and then there is some bees that are able to do very specific tasks. Of course, they can be based on machine learning and domain knowledge and optimization, but for a dedicated task. And then the LLM will transform the request from the operator by calling some specific domain knowledge, some specific application, and then integrate the result and perhaps give a kind of restitution for the operator. And once again, the natural language, perhaps we have to work on that, because in the control room, for example, they're speaking a quite strange language. They're using some fuzzy thing and some fuzzy concept, or short circuit, or shortcut in some words. They're not using the right terms that you can find in the dictionary or in Wikipedia. So you need to learn the dialect. So there is something on the ontology of the operators that also we need to work on that. So this is my what I have, and then yes, my final. So I put a kind of different kind of stuff on what I did during my career, so as a kind of joke to finish. So this is what I have. Yeah. Yeah. Yes, sure.
This is just really my lack of knowledge, and you don't have to go into this. Anyone more knowledge than me, probably a lot of you. can answer this. I'm not too familiar with GNNs. I come from more of, I know, probabilistic graphical models. How is GNNs accounting for topology? How is it topology aware in a precise sense? Because when you talk about like message passing to learn graphical policy, in probabilistic graphical models, what that message passing is referring to is you have a graphical structure where your nodes are the random variables. The edges refer to a probability connecting between random variables, so it encodes a conditional probability. So you have message passing is an inference algorithm in terms of probabilistic graphical models. Inference algorithm, which decomposes this joint probability to this conditional sum product joint probability distribution, or it's not. It's decoupled in a sense because of this graphical structure. So then a message is literally just what does the joint probability of this specific part of the graph mean. But that's not what GNNs do. Message passing is part of the learning process. So what is a message in the graph? Is it like a stepping equivalent? Is that what it's doing? It's stepping equivalent of the graph. You're learning. What is a GNN being topology aware in a powerful set?
So we have the same topology than the real system. So we mimic the topology. So we have some graph. So we have the same graph. So and then we learn how to update some kind of fictitious latent variable in the node. Yes, for example, the voltage, for example. We try to learn the voltage here. Okay. That is a combination for neural network of this latent variable in the graph. And this latent variable, we know we perform this iteration because we know that they are dependent on the neighbors. So like a Newton method, if you have a Newton method, so when we try to solve an AC power flow, we have some Newton method and we have some iteration. So this is more or less to learn the Newton-Raphson method. Okay. So more or less. So this is more.
Thank you.
So we learn how to solve the problem. It's not imitation in the sense that we learn more than we learn how to solve. So it's something.
So like architecture where you use like a DC approximation GNN to then update AP back and forth. If you just want like just use one GNN, would you give it the topology? Like let's say you know the topology beforehand. Would you just give it the topology beforehand, or would it have to learn topology?
I want to optimize the topology. I want to find the best topology.
And then say like what is the best possible?
Using a DC approximation because I'm not able to do the AC with the topology. So I decompose the problem in two steps. A linear approximation, I fix the topology, and then I try to solve the AC with all the degree of freedom I have. Not mixing everything, and it's because it's more efficient and also it's more explainable for the operators that as a, yeah, this is the main idea. Yeah. Sure. Five minutes. Yes, to solve, yeah, to optimize everything. So this is so this is to optimize all the more or less. Yeah. But for optimization, just a DC approximation, sure, yes. And not optimization of topology. We assess a few topology, we have the M-1, blah, blah, but we don't try to optimize the topology with that. The operators are more some kind of rule-based thing, and they are doing that. Or, yeah, so they change the topology based on some rules, and we want to do more than that. And the big question is how to embed the controller we have. The embedded controller is a big question that we need to take into account this controller. And for me, it's a big open problem how to, because we are pushed to a very complex MPC thing, And then I need to take into account the fact that I'm very smart and I have this very complex controller. And so we need to find some proxy or perhaps some approximation. But perhaps something that perhaps people, because we have this control layer, so perhaps if the optimization is not completely okay, we are not completely, you know, we're not completely dead. So the idea is that, yes, we have this idea of these layers that, of course, we have this control layer that will do something. So if the optimization is not, okay, did something that is not fully feasible, the controller will do something. So it's not, you know, and this controller, we want to have some guarantee and certificate. Yeah.
I had a question about that with the controller itself. Like, what is the communication infrastructure for like if an engineer wants to disconnect the line or relay, whatever language you want to use for that? Like how exactly, what is the communication method by which someone accesses that switch? Like to get right.
So we have protocol and we have all this. Yes. So in the SCADA system, so the operator can click on a button and then yes. Okay. So we have a lot of
It's like fiber optic.
Okay. More or less, because there is a lot of layer for this security and blah blah. But basically, yes, we yeah.
I saw you had some comments about like the node breaker topology control thing. I was wondering, do you have like I was asking Sarah as well as like, do you have an explicit description of the set of all possible configurations for one of those?
Yes, so we are starting to open source also snapshot in the detailed topology for, I don't know, 3 years or I don't know, 5 minutes resolutions with all the detailed topology and the status of all the breaker and everything. So, and then, but there is no injection. So it's not possible to solve the problem because, but you can see the variability of that, and we don't know why the topology. So it could be an outage to perform some maintenance, some fault, or some optimization. So we don't know. So it's just a snapshot. You have the state, but you don't know why we have this state. So we have no labeling. That the fact that we.
That's where is that located?
So I can send you the link, but but of course Mathieu is working on that with us and to create some the injection and everything.
Okay, got it. That's wonderful.
Yeah. Yes. So it took me a long time to be able to push the management to do that. So because it was very difficult. And
yeah, that's an incredibly
yes. It was more or less my last task in the company to try to do that before. It was a long discussion. So, but yes, yes, yeah, sure, Kim. Yeah. So my idea is more to have this, the idea that perhaps what could be the future is more that. So we have something that understands some concept and is able to formulate, to transform some natural language thing in some mathematical formulation, or to select the right thing. And for the users, that will be a big LLM, but in fact, it's not. It's like DALI. So the idea is that perhaps that's integrated, but it's not. And you put a lot of domain knowledge on the bees, and they are specific bees. They are not the same. And you train them to some specific task. But then there is an elephant that chooses the bees. Yeah. So but something like that. But but it's a kind of, but at least it's a vision that yes, some people believe that we just have this big elephant and that's it. No. The user could be someone in the control room or in a planning. Sure. No. Yes. Well trained or bizarrely trained. So, so because this is the problem we have, because we are many situations that are not very usual, and so perhaps there are some kind of bias, or so it's difficult because. And more than that, because we want to put some control on the things that are very obvious, and so everything that is obvious will be under the control of automatic stuff. Then the remain thing will be just very difficult to understand. And so I push a lot to have some training session where we put all these assistants in the training session to understand how they interact with this machine learning. And of course, I push also to have something that says, I don't know, or I'm not sure. So not to respond every time something. so I push to have some confidence interval, yes, or something like that, and to have this conformal prediction or whatever on top of the response to say I'm not sure, I don't know, something like that. But it's a big. But what we can do is we have a project to try to have a new training environment where we are able to put all these assistants to learn how they can interact in very stressed conditions. Because in normal condition, all the control, we do everything. or when you have very, very strange wind or solar or some strange maintenance somewhere, then perhaps this thing will not work, but then they will need to take the lead when everything is very complex. So we need to do more training, but also with the assistants and they understand the limit of the assistant. Understand, yes. And then also we can also tune the assistant around the training because for example, we can have different operators in the same scenarios. In reality, we have only so we can also have some feedback for different operators in the exact same condition to have some kind of socially guided machine learning to say yes, I like that or I don't like, but we are sure that only the operator is changing, not nothing else. So we can also perform some experiment around this training simulation to learn perhaps something more for the assistant. But now we have a big open project to build this training simulation where we are able to plug the assistant, and of course we need to have the right equation in the training, and of course we need also to have a real-time response, 1 second in 1 second for the operator. No more than that, but so we need to, yeah.
One question is with the GNNs, how much training data did you need to train your models? Was it a lot, or was it because maybe they are topology aware, you don't need as many diverse data sets to train it? Like how much of an issue is training data for you?
The data for us they are the result of some simulation. They are not the data from the field. So because because we are always operating the system around the nominal condition. So it's not enough to train, to learn. And then I'm pushing a lot to do something a bit more clever in the sampling rather than to sample randomly, to have this important sampling or something like that. So now we are using perhaps some other project. We try to use the first proxy as a Gaussian process of the complex simulation engine. And then we use this Gaussian process to select the sample. We have a sample, so okay, I use the Gaussian process, so I know if the sample is bright or not, or gray, so I just simulate the gray thing. Of of course, I need to keep a bit of the 0 and 1 also, because there is a possible mistake. Then I update my Gaussian process, and that helps for me to sample where it's important for the output, because you know, so we try to we try to do that. So to do something that is a bit less crazy than sampling randomly. So I push a lot to have this kind of loop, the sampling.
For your default, have the step where you check people. I know.
Sure.
For this, a lot of people in not only practice but also in node networks in general are like working on how do I develop a node network architecture that guarantees a feasibility to any particular optimization problem.
Yes.
Before. Were you aware of those and you just didn't want to use it because maybe it's too slow, or?
No, discrete variable. So what they are doing is very nice for continuous variable, but for discrete variable, you know, it's more. So.
I actually read a paper from the PSERC paper, and which it was with like these, you know, it's hard to map. There's a machine learning researcher in Hong Kong. Oh, Ling Wanchen. Yeah. They basically made this node network architecture that would solve optimization problems, would maintain feasibility, and team those on the paper because they use process systems as their specific example.
But
so,
I'm not sure they have discrete variables. So now we try to think about that. Yes, but first we also want to use some other possible things that are so we are looking to different possible. But what I understand, what we can do is to transform the problem to have more kind of whether to have 0 and 1, to have a to have a probability, So then we have a continuous variable on the probability to be 0 and 1. And then we can perhaps opt to have this back propagation to find the p, the probability to be 0. But it's not very clear for me. So we have some people that try to work on that. But it's not completely obvious that we can do something good. But I understand that people in machine learning are doing that. So they are more doing this kind of randomized and then hope for the best, or something more clever than that. But yeah.
We have a long time, so when you head out, you're going to change it out. How do you do the
Yeah. So yeah. If you have a question, yes, I can.